This lecture is entitled The Ear, or the Eye and the Ear. First we're going to look at the eyes. So we'll look at some structures around the accessory structures of the eye, such as the eyebrows, the eyelids, the conjunctiva, the lacrimal apparatus, and the extrinsic eye muscles. Eyebrows. Eyebrows help shade the eyes from sunlight and help prevent perspiration from trickling down from the forehead and getting into the eyes. The eyelids, or the palpebrae, are to protect foreign bodies from entering the eye and allow a mechanism for foreign bodies to be washed out of the eye when blinking. The upper and lower eyelids meet at the medial and the lateral commissures. Here you see on the picture the lateral commissure and the medial commissure. This structure here, the lacrimal caruncle, is an area at the medial commissure which contains sebaceous and sweat glands. This also aids in cleansing of the eye, helps to flush out the eye when foreign bodies are in the eye. Here's a close-up of that same picture. Here's a lacrimal caruncle, kind of the fatty area on the medial commissure of the eyelid. This is a sagittal view of the eye. A few things to know. There's the orbicularis oculi muscle is here. And again, this is circular muscle around the eye. So at this slide, it's going to look. This slide is going to look like a section muscle up above and then below. But remember, this is a continuous circular muscle going around the eye. So when it contracts, it's going to squeeze, it's going to narrow this eyelid and close the eye or wink the eye. This is the palpebral fissure here, the area between the upper and the lower eyelid. What is the conjunctiva? The conjunctiva is a transparent mucous membrane that lines the eyelids and folds back over the anterior surface of the eyeball. It covers the white of the eye. The white of the eye is called the sclera. The conjunctiva covers the white of the eye. It does not cover the cornea. The cornea covers the pupil, and it comes in contact with the conjunctiva. But the conjunctiva is actually the covering of the white part of the eye only. The function of the conjunctiva is to produce a lubricating mucus to help prevent the eyes from drying out. Here we see the conjunctiva here. It's the surface over the white of the eye. Mucus secreting surface over the right of the eye. As opposed to the cornea is over the visual part of the eye, the part that lets light into the eye, into the retina. This is covered by the cornea. The lacrimal apparatus is the lacrimal gland and the ducts that drain lacrimal secretions into the nasal cavity. Basically, it's tear ducts. Here we have the lacrimal gland here in the lateral superior portion of the eye. It drains into the eye, flowing this way, and then there's a punctate, lacrimal punctum here, and you can see this hole in your own eyelid. That drains the tears, drains into the nasal lacrimal duct, and goes on into the nose. That's why when you cry, your nose is runny. Eye movement is controlled by 6 extrinsic eye muscles. Okay, they originate on bony surface and they insert on the eyeball itself. And they're able, when they contract, muscles pull, not push. When they contract, they pull the eyeball in a certain direction. There's 4 rectus muscles. There's superior rectus, an inferior rectus, a lateral rectus, and medial rectus. And there's 2 oblique muscles, a superior and an inferior oblique muscle. Here's a diagram showing a good picture of the inferior part of the lateral rectus muscle. This is the lateral, so this would be looking at the right eye from the right side. So this is lateral. This is lateral rectus. So when this muscle contracts, it's going to rotate. It's going to pull the eye laterally. It's going to pull it towards the lateral side of the face toward the ear. This muscle is innervated by the abducens nerve, as you recall. And remember, abducens and abduction kind of sound the same. And the abducens nerve simulates the lateral rectus muscle to abduct the eye. Now on the opposite side of the eye, there's a medial rectus muscle. You can't see it here in total, but this is part of it here, and it does the same thing. It attaches to the other side of the eyeball. When it contracts, it's going to turn the eyelid in towards the nose. It's going to be medially, and that muscle is controlled by the oculomuscular muscles. The superior rectus is here, and this attached on the upper surface of the eye. So when it contracts, it's going to raise the eyeball upward. This is also controlled by the oculomotor nerve. This is the inferior rectus muscle. Again, it attaches on the lower portion of the eye. When it contracts, it's going to lower the eye. It's going to look down towards the ground. And these oblique muscles. See how they attach obliquely? So when that muscle contracts, it's going to rotate the eye, and it's going to rotate the eye. It's going to cause the eye to look upward on the superior part on this inferior oblique muscle. When it contracts, it's going to pull the back of the eye downward, which is going to make the front part of the eye go upward. And it's also going to rotate it. And the superior oblique is going to do the opposite. When that pulls, it's going to rotate the eye in a clockwise manner, looking from front, from anterior. It's also going to pull back on the back part of the eye and cause the eye to look downward. Here's another view of the extraocular muscles. And this shows the lateral rectus muscle and the medial rectus muscle very, very good here. And you can imagine that muscle contracting and tilting the eye, looking towards the nose, and then the lateral rectus contracts and turns the eye towards the ear. You have the superior rectus, a good view of it here. Think about that muscle. When that contracts, it's going to pull the eye upward. Since it's actually pulling at an angle, it's going to rotate the eye, so it's not going to look straight up. It's going to look up and outward some. To compensate for that, the oblique muscles counteract the angular movement of these superior and inferior rectus muscles. So this summarizes the movements. The lateral rectus muscle moves the eye laterally. It's innervated by the abducens cranial nerve number 6. The medial rectus moves the eye medially, and it's innervated by the oculomotor nerve, cranial nerve number 3. Superior rectus elevates the eye and turns it medially. The inferior rectus depresses the eye and turns it medially. The inferior oblique elevates the eye and turns it laterally. Superior oblique depresses the eye and turns it laterally. So if you want to look straight up, you have to use a combination of two muscles. You have to use the inferior oblique and the superior rectus, because both of these muscles elevate the eye. Superior rectus turns it medially. The inferior oblique muscle turns it laterally. So when those are used together, it looks up, not medial or laterally, but in straight lines. It looks straight up. So looking straight up involves the use of two extraocular muscles. Looking straight down involves the use of two extraocular muscles, the inferior rectus and the superior oblique muscles. And remember, the superior oblique muscle is innervated by the trochlear nerve, cranial nerve number 4. Clinically, this extraocular muscles can be tested by just having the patient look at your finger, move your finger up in the different quadrants, up in the right, turn it inside, follow the fingers left and right, up and down, and then that would test really all of the different extraocular muscles. If all the muscles are intact, then there should be no problem moving the eye it left and right and up and down. The structure of the eyeball has 3 layers. There's a fibrous layer, a vascular layer, and an inner layer. The internal cavity is filled with fluids called humors. The lens separates the internal cavity into anterior and posterior segments. Here's a picture of the lens separating the posterior segment from the anterior segment, separated by the lens. Now I've said the eye is made of 3 layers. The outermost layer is the fibrous layer. That's the dense avascular connective tissue. There's 2 regions. There's the sclera and the cornea. The sclera is the whites of the eyes. It protects the shape of the eyeball. It anchors extrinsic eye muscles. It's continuous with the dura mater of the brain posteriorly. That's the whites of the eye, sclera. The cornea is a transparent portion. It bends the light as it enters the eye. This allows light enters here because this allows you to see. Light goes through the cornea, through the lens, and it's focused on the back part of the retina, where the optic nerve then sends the image back to the occipital lobe. Here's a picture of the cornea. Again, this is a transparent. In real life, here this is kind of light blue, but in reality, it's transparent. And here's the sclera, the white part of the eye. See how the sclera is kind of continuous with the cornea. It's just over the pupil. When it gets over the pupil is the hole here in the iris where light goes in. As it gets over the pupil, the sclera transforms into the cornea and then returns to become sclera again. The pigmented layer has 3 regions: the choroid, the ciliary body, and the iris. The choroid region supplies blood to all layers of the eyeball, and it's a brown pigment that absorbs light to prevent light from scattering and increases visual acuity. Here's the choroid here. It's the second layer. The outer layer is the sclera. Next to the inner layer is the choroid. And the vascular, this is considered the vascular layer. And it's continuous with the ciliary body and the iris. The iris is the colored part of the eye. And it has a hole in the middle called the pupil. And the ciliary body are these muscles on either side of the lens. It's a circular muscle, kind of like the orbicularis oculi was. It's circular, so it looks like it's a muscle here on top and on bottom, but actually it's reality circular muscle. It circles around the lens. And that muscle, when it contracts, it changes the shape of the lens, and that helps focus the light towards the back of the retina to get better vision. This is what I just said. The ciliary body is a ring of tissue surrounding the lens, and it controls the shape of the lens, so it focuses light. The iris is the colored part of the eye. The pupil is a central opening that regulates the amount of light entering the eye. There's 2 muscles that control the size of the pupil: the sphincter pupillae and the dilator pupillae. This shows the middle portion. There's the choroid plexus, the ciliary body here, and the iris here. Shows those the 3 sections of that middle layer. Here's how the eye pupil changes shape. There's a sphincter pupillae. That's a sphincter muscle. When it contracts, the pupil gets smaller. There are also fibers that pull the muscle outward, or pull this pupillary muscle outward, and when that contracts, it dilates the pupil. That's what's called the dilator pupillae. This is controlled under sympathetic autonomic nervous system control. Parasympathetic nervous system control controls the pupil sphincter, so it makes the pupil size decrease. We'll discuss more of this in the lecture on autonomic nervous system. We just remember the iris has 2 muscles: the sphincter pupillae and the dilator pupillae. The sphincter closes the pupil, makes it constrict. The dilator dilates the pupil. Now the inner layer, main component of the inner layer is the retina. The retina is an out pocket of the brain, so the retina is actually nervous tissue. or it's actually part of the brain that's extruded out into the eye socket. It absorbs light and prevents it from scattering, and it stores vitamin A. So vitamin A is important for vision. Here's the retina. This is the third layer, the inner layer, retina, and that lines the cavity, the ocular cavity. This structure here is called the posterior segment. It's called vitreous humor. This is actually a liquid. It looks like a solid on this picture, but it's a liquid, and it fills this posterior chamber. So the inner neural layer is transparent. It's composed of three types of neurons: photoreceptors, bipolar cells, and ganglion cells. And here's the sequence of events. Here's the photoreceptors here. They're in terms of rods and cones. Rods and cones. Then you have the bipolar cell layer, and then the ganglion cell layer. And this is the retina. So light comes in, says from the pupil over here, the pupil right here, light comes in this direction and hits the back of the retina. So it hits, light enters and hits this part here. Since this is transparent, it goes on through these two cell layers, and it interacts with these photoreceptors, the rods and the cones. They then in turn send a electrical impulse to the bipolar cells, which then send the impulse to the ganglion cells, which then send their fibers down through the optic nerve to the visual cortex. So you have the photoreceptors activating the bipolar cells, activating the ganglion cells, which then stimulate the visual cortex. This optic nerve is a bundle of nerves exiting the retina on its way to the visual cortex. The optic disc is the blind spot. Now that's the site where the optic nerve leaves the eye. It lacks photoreceptors. So if I look back at the preceding slide, the optic disc is the area here. So this is the retina. All this retina. This retina is areas that you can have photoreceptors and you can see through this area. But there's no photoreceptors beyond the optic nerve because the nerve is there. So the nerve actually prevents the vision can't be obtained from the optic nerve itself. It has to be obtained by the photoreceptors, and there are no photoreceptors in the optic nerve. So this optic nerve creates a blind spot in each of the retinas. I mentioned the photoreceptors are rods and cones. Rods are vision receptors for dim light. They're peripheral vision receptors. They do not provide sharp images or color vision, so they're kind of the black and white, vague, shadowy images you see in your peripheral vision. Cones, on the other hand, are visual receptors for bright light. They have high resolution. That's when you're looking at something, you want to get the clearest view at it. You get a color, high definition view. That's through the cones. There's an area in the retina called the fovea centralis. It's an area of the retina that's mostly cones, and it's the point at which you have the clearest, most acute vision. When you're looking at something, at an object, and you want to get the clearest view of it, your eyes automatically rotate your retina and your ocular region so that the fovea centralis lines up with whatever the object you're looking at, and to give you the best optimal vision of all. Here's a picture of the macula lutea, or the fovea centralis. That's the area where the density of cones is the highest. This is a high visual acuity area here. This is the optic disc. This will be the blind spot here. This is where the optic nerve exits the retina. All these are blood vessels. The retina is the only place you can actually see blood vessels and directly see blood vessels at work in the body. You see this through an ophthalmoscope, and you can see evidence for diabetes and for hypertension and other disorders just by looking at the retina, particularly the vasculature from the retina. Internal chambers of fluids. Remember, there's anterior and posterior segment. The posterior segment has the vitreous fluid, vitreous humor. Anterior segment has aqueous humor. Now, just so you don't confuse, there's posterior segment and anterior segment. The anterior segment is made up of two chambers, anterior chamber and posterior chamber. So the anterior chamber and posterior chamber are both part of the anterior segment. The anterior chamber is between the cornea and the iris. The posterior chamber is between the iris and the lens. So there's space in between those two. And the posterior segment is behind the lens. The vitreous humor in the posterior segment basically adds support to the retina. It's a fluid filled area, so the fluid acts as a hydraulic pressure, intraocular pressures, which holds the retina in place. And you see here how the vitreous humor of the posterior segment kind of fills this face up, and that would keep the retina pressed back against the outer edges of the orbit and of the eye. Here's the anterior segment. Again, the anterior segment is composed of the anterior chamber and the posterior chamber. Anterior chamber is between the cornea and the iris. Here's the cornea, here's the iris. The iris is the colored part of the eye. That's the anterior chamber here. The posterior chamber is between the iris and the lens. Both of those are considered the anterior segment. The posterior segment is behind the lens. Here's a cartoon of the ciliary body. Remember, the ciliary body is a circular muscle that goes around the lens, and when it contracts, it can stretch and bend the lens to focus light. It acts very similar to the to the orbicularis oculi muscle. And when it contracts, it's a circular muscle. It's a sphincter type muscle. The anterior segment contains aqueous humor, just like the posterior segment contains vitreous humor. This supplies nutrients and oxygen to the lens and cornea and to the retina. It removes waste, and the fluid is circulated through this anterior segment. If it gets blocked, then it can cause an abnormal pressure buildup in the retina, and that can lead to glaucoma, and that can cause compression of the retina and optic nerve. Remember, nerves are very susceptible to pressure, and so if they have a buildup of pressure inside the eye, that can cause damage to the nerves and would lead to vision disturbances and blindness. This just shows the flow of aqueous humor. You don't really need to know the pathway. You just know the aqueous humor flows. It's similar to like cerebral spinal fluid, how it flows from one chamber to the next, one ventricle to the next. The aqueous humor has a flow pattern as well. And if it gets blocked in there, then if it got blocked at this point, then down upstream from that, it would increase pressure, and that would cause nerve damage from pressure buildup, which is called glaucoma. Now let's look at the lens. The lens is biconvex. Okay, it's a biconvex means it's shaped. It's a convex side on both sides. Biconvex shape. Back up a couple of slides. It changes shape to focus the light on the retina. A cataract is a clouding of the lens. This is a consequence of aging, of diabetes, of heavy smoking, and frequent exposure to intense light. This becomes more common as you get older. You have clouding of the lens, and cataracts are very common in the elderly. Here's a few more information on clouding of the lens, some of the causes and some of the treatment for clouding of the lens or cataracts. It shows the lens, the biconcave shape of the lens. This lens is clouded, so this is a picture of cataract. This lens is not clear. It's kind of cloudy, opaque appearance. We'll talk about light refraction, and this has been normal eye. If you have an object that you're looking at, that the image from that, the light from that object is reflected back into the cornea, and it's picked up by the retina. Ideally, for the best focus and the best clearest view, you want to have the image of what you're looking at projected right along the surface of the retina, so it can be picked up by the photoreceptors. To do that, the light has to be manipulated by these lenses and by the cornea. The cornea and the lens both bend the light so that the light is angled and so that it's directed to the back of the retina. Now, in normal situation, the ciliary body can contract, and the lens can make adjustments and focus, and that happens until the lens gets thickened with cataracts, and then the lens is less compliant. It's harder for the lens to change shape. It's harder to focus. That's why as you get older and the lens gets firmer, you need glasses for near vision, because you can't change the shape of the lens to accommodate for near vision. You need reading glasses. Let's look at a couple of differences here. This is normal, how the light is reflected to the back of the cornea, the back of the retina, to get the clearest image. If you have farsightedness, you have this is uncorrected here, without glasses or without contacts. Light comes in, and instead of being directed to the retina, the focal point is actually at an area behind the retina. Well, there's no photoreceptors back behind the retina, so this results in a blurry image. So to correct that, you use a convex lens, and then that refocuses the light so that it focuses the light on the posterior surface of the retina, so you have a clearer focused image. Now, similar happens with nearsightedness. In nearsightedness, this is without glasses or contacts. The light is reflected not on the retina, but in an area in front of the retina, and so the light is reflected at that point. And when it reaches the retina, it scatters out, and it's not focused to have the optimal shape of the image on the retina. It's in front of the retina. But with proper corrective lenses, either contacts or glasses, again, they adjust the shape of refraction of the light so that the image is projected to the surface of the retina. When the image is projected on the surface of the retina, that gives you the clearest view and the clearest vision. It's an interesting experiment you could try if you wear glasses or contacts and you lose your glasses or contacts and you need to be able to see. If you look through a pinhole, or you can make a pinhole from your finger, or use a pen, poke it through a piece of paper and just look through a pinhole. When you look through a pinhole, it allows only the fibers or the light waves that are right in the middle to go through. So if the pinhole is here, these other would be blocked by the area that's not the pinhole. So only the light goes through the middle of the pinhole. And so if it's uncorrected, the pinhole would just allow this light in the center, very center of the pinhole, to go through. And even though the light and hole is focused on the back, that light has to go right through the retina, so that lines up directly with the retina, both on far-sighted and also nearsighted. There's only that center wave of light goes back and hits the retina. So the bottom line is, with a pinhole, you could see basically 20/20 without the use of glasses or contacts. Now, it's going to be a dark image because you're not letting a lot of light in the eye, but it does give you a clear vision. So if you're stranded on a desert island and you don't have your glasses, and all you can do is make a pinhole to look at, you can read the instructions on the FedEx box and maybe get you rescued. Here's an exercise you do to check your blind spot. Remember, blind spot is where the optic nerve exits the retina. Cover your right eye and look at the black star, and slowly move towards the screen or towards the paper when you print this out, and then the colored star will disappear. And that's when the colored star lines up with your blind spot. It literally goes away, illustrating that you have a blind spot. Now let's move to the ear. The ear is for sound and balance reception. There's an outer ear, a middle ear, and an inner ear. The outer ear is composed of the auricle, the external acoustic meatus. Remember, this is the canal that goes through the temporal bone. The external acoustic meatus goes from the outer ear down to the eardrum, or the tympanic membrane, eardrum. This is all considered the outer ear. The middle ear are these ossicles, or small bones of the ear. They're the malleus, the incus, or stapes, commonly known as the hammer, anvil, and stirrup. And there's a pharyngotympanic tube, which is right here. This is the eustachian tube. That's what connects the inner ear, or probably the middle ear, to the back of the throat. This is when you're flying on a plane and your ears stop up and pop, and you have to chew some gum for them to pop out. It's because the pressure builds up inside this middle ear area, and it's closed off by this eustachian tube area. And by chewing, it relaxes this tube and equalizes the pressure so that your ears pop and you can hear again once the pressure inside the ear normalized with the outside pressure. The inner ear is composed of semicircular canals that you see here. And I've got a larger picture to show you in just a minute. And the semicircular canals are balance organ, and that lets you know, kind of helps you to keep your balance. And the cochlea is this spiral, looks like a snail. It's curled up. That's the hearing organ. And both the cochlea and the semicircular canals are filled with perilymph, which is like central cerebral spinal fluid, and it's filled with fluid inside this inner ear structure. This shows the cochlea. Sound hits the tympanic membrane, and then that sound is transferred from the tympanic membrane to this oval membrane, oval window, which is actually connects to the cochlea through these three ossicles. The ossicles amplify the sound waves. Because sound is conducted through this bone, and basically, as the eardrum moves in and out, it's going to move this stirrup or stapes bone in and out, and that creates ripples inside the cochlea. These ripples are ripples of the perilymph fluid, and the lining of the cochlea is full of little hair cells. These hair cells detect the movement of the fluid, so there's certain hair cells that all along the cochlea, and depending on which hair cells are stimulated, that's translated into certain frequencies of sound. Sounds at different frequencies stimulate different hair cells along the cochlea. And part of our hearing process is learning what those sounds, how to interpret those sounds. That's the process of learning as much as anything. So the sound waves vibrate the tympanic membrane here. The auditory ossicles vibrate, and it amplifies the pressure that's received at the tympanic membrane, amplifies that pressure here on the oval window. Pressure waves created by the stapes pushing the oval window through the fluid to this vestibule, scala vestibuli. That's just the opening portion of the cochlea. Sounds with frequencies below hearing travel through the helicotrema and do not excite the hairs. Since they don't excite the hairs, that's why it's below hearing level. Sounds in the hearing range go through the cochlea and vibrate the basilar membrane and deflecting hairs on the inner hair cells. So once the hairs are deflected, that allows you to hear the sound waves. Those hairs are connected to the nerves that form a vestibulocochlear nerve, cranial nerve 8. This picture is to illustrate. This is the cochlea, as if you, instead of it being coiled up, if you were to open it up, straighten it out, and then transfer sound waves. Sound waves would have certain areas where they would be certain frequencies and amplitudes, and this is all the surfaces picked up by hair cells. So hair cells in this area would detect this waveform in here. It would detect waveform here, and your brain over time, after it learns what these sounds are associated with, it can learn to interpret the sounds. This just shows that different frequencies of sound result in the stimulation of hair cells at different areas along the cochlea. The lower the frequency of sound, the lower the frequency of sound, the higher the wavelength. So the longer it would be before the hair cells are stimulated by a low frequency sound. High frequency sound, like this, has a short wavelength, so therefore it's picked up at a shorter distance from the opening of from the origin of the cochlea. And the semicircular canals work in a very similar fashion. Notice that the semicircular canals are at 90-degree angles from each other, and they're in the X, Y, and Z axis. So they have horizontal, vertical, up and down and back and forth motion. And these are lined with hair cells as well, and fluid is inside here. So when fluid flows in one direction, it's picked up by the hair cells, and that sends a signal to the brain that your head is moving in a certain way because it's picked up the fluid moving in that certain direction. Just notice that these semicircular canals, there's one in anteriorly, there's one posteriorly, and there's one laterally. And so that those three orientations allow you to move your head up and down, side to side, and left to right, or and rotationally. So all 3 degrees of all three dimensions in 3-dimensional space, you can pick up sound, or you pick up waves in semicircular canals, and helps your balance, and helps let your brain know what orientation your head is and your body is. When this goes bad, it's called labyrinthitis or inner ear problems. That's a cause of vertigo, or a feeling of like the room is spinning, or you're spinning around in the room.